Hello, everybody. Today we're going to be talking about the final aspects of analyzing motion through potential and kinetic energy in a gravitational field in a little more detail and defining something we call escape velocity. So I think I'm gonna start with escape velocity. What we discovered yesterday, also in the last video, is that if you have some mass like the Earth and you have something that has some initial speed, then obviously it's going to gain potential energy and lose kinetic energy. Now, gaining potential energy means it's coming out of the potential energy well, and we're going to graph this in a second. That's part two. So we start at some R naught. Obviously, this has some radius R naught. And what we would do is say, okay, this is progressing this way on the graph. It's starting here, it's progressing up. And the question is, does it get to zero? What is the total energy? And how does that tell us about what happens? Well, the point is, it tells us everything about what happens. What we discovered yesterday is that if E total is greater than zero, that means the kinetic energy is bigger than the potential energy well, which means that I'll do that as initial, right? The kinetic energy initial is bigger than the potential energy well, and therefore it escapes, right? It has excess energy, it has excess kinetic energy. Because remember, the potential energy is the work gravity would do taking energy away as it comes out of the well. Obviously, if you start up here and you drop something, if you drop something, it's never going to escape. It's always going to fall back. If you drop something, it always is going to have negative energy, right? I don't know where I'm going to put that. I'll put that here, right? E total is less than zero, means that KE initial is less than negative potential energy, right? This is the work gravity would do. It's also the work gravity can do. That says would, believe it or not. Maybe I'll write that a little more clearly. Work gravity would do is potential energy. It's also the maximum amount of work gravity can do, which means if you have tons of excess energy, gravity can only take away so much. That force can only remove so much of it. That force decreases, is what we talked about yesterday, right? That force decreases, and so it can only take away so much. How much? Well, that's what the potential energy measures. We know how much. How much energy can this take away? That's what we have a formula. It's negative GMM over R, not minus negative GMM over R, final, right, that whole thing, or backwards, right? Final minus initial. Anyway, so do we have enough energy to come out of this well? Well, we do if we have enough kinetic energy, and that means E total is, because kinetic energy is positive and potential energy is negative. So the question is, which wins? Careful, and obviously this is gravitational potential energy is negative because it's attractive. It's a binding energy. So which wins? That's the answer to the question of what happens. So great. Obviously, if I drop something, I'll finish that line of thought. The initial velocity is zero, and the potential energy is initially, that means the initial kinetic energy is zero, which means there's no positive to cancel out the negative, which means the initial energy, negative GMM over R naught, wins. Obviously, E total is negative if you drop something because it just is negative potential energy. It's going to be attracted inward. speeding up on its way in, and it's going to gain kinetic energy, get more negative kinetic potential energy, and it's just going to fall toward the mass. So escape velocity occurs when E total equals 0 precisely. So this is greater than 0. This is less than 0. Obviously, there's a perfect point in the middle where it either doesn't escape or it does escape. And the escape velocity is that exact moment where kinetic energy initial equals negative potential energy initial. And if that's the case, clearly then kinetic energy plus potential energy equals 0. So E total equals 0. And we have it perfectly canceling. What's going to happen here is really cool. Graphically, what's going to happen is that our E total is going to make it such that the object starts out at some R naught. It's going to come out and it's going to asymptotically approach 0. V final will asymptotically approach 0. Here, sorry, I'm going to write it like this. V will asymptotically approach 0, whereas in here, if there's excess kinetic energy, V will approach some V final. There's going to be some excess speed that it's going to asymptotically approach. And we'll graph that in a second. We're going to graph all these today. So, great. Just going to leave it there. I could talk more. But here, this situation is where I have a mass, I have an object that shot up at some initial speed, and it goes up, it slows down, it slows down, it slows down, it slows down, but it slows down forever. It never actually turns around. It's like the cusp of where it's slowing down and it's approaching 0, but it never actually gets to 0, because to turn around, right, this will eventually reach some final velocity of 0 and then drop or fall back down. If you have energy less than 0, it's going to eventually come back. This one will never come back, and V will approach some V final. And this one is where V never actually gets to 0, but it asymptotically approaches it. So do you see the difference between these three? I hope that makes sense. If not, please rewind. That's the difference between these three of what happens at the end, what happens to V final. And that story is told entirely in E total, which is so cool that that number tells us everything. So what we can do is pretty straightforward. We can set 1/2 mv initial squared equal to g m over r naught. Remember, setting kinetic energy equal to negative potential energy. This will make E total equal to 0. So we start here, we go here. We know that this will end up in V final approaching 0, right? V approaching 0 as a V final. And so therefore we just plug the equations in. Great. And we end up getting is that V initial, I multiply by 2, divide by m, I get is the square root of 2gm over r naught. And we call that the escape velocity. If I plug in the mass of the Earth and I plug in r naught is the radius of the Earth, I get the escape, I believe is 11.4 kilometers per second. We'll do that in class. We'll calculate it. I'm just trying to remember that off the top of my head. That's the cusp. If I go 11.3 kilometers per second, I jump 11.3 kilometers per second. I have my super shoes on. I will go up. The force will take away energy from me. I will have initial velocity. I will have a slower velocity, slower velocity, slower velocity, and eventually I will stop, such that I will have some final R final. My kinetic energy final will be 0. My potential energy final will be negative GMM over R final. And my initial kinetic energy, of course, is 1/2 mv initial squared, where I can plug that in. And my initial potential energy, of course, is negative GMM over R initial. All of this is known, and I can solve for this. So I can solve for how far I went off the Earth. And obviously, this is your first homework question. I'm giving you the information. I'm not going to do this because you're going to do this for homework, but you know how to set up equations. You know how to plug stuff in. Just be very mindful to do it appropriately. Don't forget these negative signs and you'll be just fine. But the concept, of course, is this. If I have 11.8 kilometers per second, I go on forever. This is the cusp. I think it's 11.4. I'm hoping I'm right on. It's around there. Cool. That's escape velocity. So let's do some graphs. So the first graph is F versus R. And let's do it for an escape. Let's say initial velocity is 20 kilometers per second. F versus R. Let's also do potential energy versus R and kinetic energy versus R. So this we're definitely going to escape. And if I want to graph force versus R, I know the equation is negative GMM over R squared, and that looks like this. So what you want to mark, I'm doing this a little less detailed than maybe you should, but you're going to want to figure out your R naught. You're going to want to figure out your R final, or maybe your R final goes to infinity because it escapes here. And you're going to mark this here, and you're going to say my object follows this path. Right? My initial force is here. You don't necessarily have to solve for it. Your initial force is here, and it comes out. So the force is always pointing against the motion, but it doesn't take enough energy away. So that's the force versus R. Now the whole point is this is the negative slope of potential energy. So here we have a very negative value, big negative value, big inward value, which means, of course, and we already know the shape, so this is a little redundant, but it's helpful to remind ourselves, especially when we do new things, that our initial potential energy is here, our initial is here, and that means we have a big negative potential energy. So big negative potential energy corresponds to, big, big negative force corresponds to big positive slope for potential energy. And we happen to know that it's negative because it's attractive, right? And we went over this in class on Tuesday. And of course, the slope decreases. What does that represent? That represents that the force decreases, right? Right. So the slope gets less positive, which means the force gets less negative. But remember, negative force just means inward. Right? That's what the negative means. That's why I like drawing it here, right? It kind of reminds me. So once again, here's a force pointing in, force pointing in. Here's my R naught. And of course, my path is the same, and this is going to escape. E total is greater than 0. So escape goes away. Sorry. It does not go above 0. The energy approaches 0 forever. And it leaves with some excess speed. So this is not that neat on my little pad here. I could probably do better, but you can definitely do better if you just take a few minutes and draw this nice and neatly. Anyway, so cool. What does kinetic energy look like? Well, kinetic energy looks like this. Let's see if I can fit it in here. I'm gonna fit it in here. So kinetic energy is always positive, which is fun because potential energy for gravity is binding, so it's always negative. There are some potential energies that are positive, but not for gravity, right? Potential energy for gravity is attractive, binding, so negative. Kinetic energy is always positive. Great. So here I'm doing gravitational potential energy versus R, force of gravity versus R, kinetic energy versus R. Kinetic energy starts out at R initial at some V initial, and it slows down. And does it approach 0? Does it go negative? what happens? Well, if you remember, is we have excess energy. So KE approaches some KE final, which we calculated yesterday, right? We calculate the final speed is asymptotically approaching some non-zero value because the force is not enough to slow it down to zero. It doesn't turn around. It doesn't ever stop. So it starts off at some KE initial, and it approaches some KE final as an asymptote like this. Such if I add this graph and I add this graph, I get a flat line constant E total. And in fact, that flat line is this line. Because PE final, of course, approaches zero. By definition, it's binding energy, which approaches zero at infinity, right? We have zero interaction at infinity by definition, by our conceptual analysis of gravity, right? E total is KE final because we have no potential energy at the end. What form does the E total take at the end? It just takes kinetic energy. So if I added this graph and this graph, I would get this flat line here. Isn't that cool? So they both, this approaches zero, this approaches this, which means the entire time the energy was this. Cool. I'm moving on. Pause it if you need to. That's the analysis. And that's kind of what I want you to write. I want you to like write all those things. If that was the question. If that was the question, that's what you're going to write. Right? You're going to get different questions. So you're going to write different things. But just giving you an example of that's the conceptual description of the graphs. So what if I wanted to graph A versus T and V versus T for V initial equals 20 kilometers per second, where the initial radius was the radius of the Earth, obviously on the Earth. A rocket leaving the Earth and it's going to escape forever. So A versus T is going to look like this. So first of all, acceleration is negative and velocity is positive. I would say draw your diagram, draw your initial velocity, your acceleration is negative, your velocity is clearly positive the entire way. There are going to be situations where that might not be the case, but in this case, it's that way the entire way, right? So A versus T starts off at some A initial value and clearly decreases. Why does it decrease? Decrease in magnitude, because remember, decreasing, it's a vector, right? Decreasing in magnitude because A goes as F, which goes as 1 over R squared, right? A equals F over M, which is GM over R squared. That's little g, right? So A basically is little g. We're graphing little g versus time, right? So as this approaches infinity, it's going to asymptote to zero. Now, technically, I should call this T0 because this is not a graph of versus R squared. I know I have R squared here, so careful. I know the pattern looks like this, but this is with respect to T, where this is with respect to R. That's why I do this less often, and it gets a little tricky. But the reason I'm doing this is because remember, A is the slope of velocity. Acceleration is the slope of velocity with respect to time. So what does this look like? Well, here I think this still looks like this because it decreases faster first, and then it asymptotically approaches zero. Clearly, as we're going up, as R approaches infinity, the acceleration approaches zero, but also as T approaches infinity, acceleration approaches zero. Right? And A and G are the same thing. I'm kind of like using them synonymously because we're talking about gravity. So I think the shape of this is the same, relative. It's not an inverse T law. It's a little different, but it's going to look something like this. So this is a qualitative estimate. Whenever I have you guys do something like this, that's a little challenging versus time, you actually will need some really good math to be able to get the exact thing. And I don't really want to do that right now. You need parametric equations and integrals and derivatives, and we don't want to do that. We don't have the tools to do that. I don't need us to do that. This is not a calculus-based class, but what I love doing is doing it anyway without those mathematical tools because conceptually we can do it. And we don't need to limit ourselves just because we can't take the extra step to prove the math. Let's do the concept first and then realize the math is there if we want to do that as a bonus or if we want to do that later. Right? I'm not expecting you guys to do the exact equation here. So, but we are expecting to do the exact equations for energy because we know those equations. So, what we do know is this. So here the slope is negative, and large. So here velocity is positive, some initial velocity at some initial time, and it's going to decrease. And we have a negative large slope. Here we have a negative small slope. So here we have a negative small slope. So what does the velocity do? This. Now careful. Aha. Actually, let me take a step back. The velocity approaches some final velocity, right? We have excess. So conceptually, we know this. And so therefore, the final small slope will not be at zero, but will be somewhere here. So it's going to look something like this. This is probably not as perfect as I want it to be, but I think it gets the point across. That it steadily decreases. The slope is the acceleration. What is it? Negative large slope, negative small slope. Please label this. Things like this, things like this. Let's put it in pink. I want some pink. Or lavender's good enough. Right? Please label these types of things. Please label the connections. Also label the numbers if we have them, right? Label these numbers if we have them, connections and numbers. But really, I'm looking at, can you conceptually derive this graph without math? Can you conceptually see what's happening to acceleration and velocity and show it graphically and connect it to the picture that this velocity is steadily decreasing and approaches some final speed that is not zero? If this is greater than the escape velocity, and connect it to the energy. That this acceleration approaches zero from the negative realm, but the velocity approaches some final speed. That's the concept here. Rewind the video if not something didn't make sense. That was it. That's good, complete analysis of our motion through space. Obviously, there's different questions we can ask. That was just one example, but that was the comprehensive detail we're looking for when we open this up. There's always more we can do, but I think that's a good place to start for what we're doing right now. Always ask questions, email me. I love it. I love talking about this stuff with you guys. Have a beautiful day. See you in class.